Okay, here we go with this is our puzzle book here, and we'll be doing page 45. We'll start with 17. Yet before going over 17, 18, 19, 20, before tackling those puzzles, let's talk a bit about where we're at, where we're going, right? It starts with axioms. Actually, it might start even lower than that, more fundamental and more basic than that with primitive notions. Because axioms are statements, and primitive notions, well, those are almost like just words, just ideas. And usually it takes just one kind of sound, one few syllables, one word or two words to express an idea. So that's why you kind of have primitive notions, which can also be considered like undefined terms. They aren't really defined. And our undefined terms are objects like points or a set, or I should say point. Once you have one, you can have as many as you want. The plural's easy after that. This is undefined, plain. And then another primitive notion might be like a relationship, how we think of these objects relating to one another, like incidents or betweenness. And these are building blocks of this huge construction, this massive city of imaginary things that we can think up and prove to be true. But before we have statements that are proven true, we have to have statements to start with. Unproven statements, just accepted as true. And we want a minimum number of those because the game is all about proven stuff. And we don't want a lot of axioms to start with. These are unproven statements. And so this here, this is like the foundation for the plane geometry puzzles we're doing. And then on top of that, we have theorems. If your theorem's really useful, it gets known with a name, usually by your name, and then theorem, maybe. Or if they're just really general, if they're just powerful, if they're very useful, they just come to be known by a common name or maybe a name having to do with their properties, like alternate interior angles theorem. That's a theorem. And you write theorems to win games. And when you write theorems, now you have these statements to help you prove other theorems. Just like to get the very first theorem, you have nothing but axioms. That's it. You have axioms and you got logic and you have these primitive notions, these undefined terms. No one is going to ask you to define what a point is or a set. And we start with these axioms and logic, nothing else, bare minimum, very basic. And then we start proving statements, and those are our theorems. Now, kind of all over, once we have one theorem, we can easily get to two theorems, and then theorems build upon theorems, and it just becomes a bigger and bigger Euclidean space. You just build this universe, this geometrical universe, and anyone can come up with their own axioms. It's all a big fantasy, as it turns out. It seems like these things are true, but we can't really be so sure. It's amazing how how much they do seem to be true on the surface or locally in a small space. But this is how we build the things. Axioms, primitive notions. And throughout, from the very bottom here, these primitive notions allow us to make definitions from undefined terms, things that have no definitions. And this is also kind of very high level, even though it's very basic. Something like a circle is the set of all points equidistant from a given point. And a parabola is a set of all points equidistant from a given point in a distinct line. So those are something of human creation. So you can define whatever. It's using this word let. Okay, and before we get on to 17 and 18, we have to know some things about these theorems and some words. Let me get to, I need a fresh pencil. Here we go. Okay. Transversal. And we have a definition for that. We don't have one for point or plane, but there we go. We have two lines. Let's call this one L, and let's call this one M, and we'll call this line T. We'll call it T. Why do you think? T for transversal. That's right. And when you have a situation like this, you have special pairs of angles. Special pairs of angles. Now, L and M, they don't have to be parallel. They don't have to have any relationship to each other than being coplanar. They must be in the same plane. I mean, you can't have, L can't be going along this way and M, be like along the pencil pointing that way. So they got to be in the same plane. So you have two lines, two coplanar lines. It's like if points are collinear, they're on the same line. If lines are coplanar, they're in the same plane. So if you have a couple lines, couple coplanar lines, and they're intersected by another line, we call that line a transversal. And when you have one of those, you have these special pairs of angles. For example, this angle here and this angle here, because they're on opposite sides of the transversal, we'll call them alternate, because they're on opposite sides of our transversal. Let's make the transversal orange. Well, these are alternate. Because they're inside, they're between L and M, we'll call them alternate interior angles. Alternate interior angles. And likewise, there's alternate exterior angles. That angle there and that angle there. Those are alternate exterior angles. And then, of course, there's corresponding angles. I will not point those out. So alternate interior, this also is a pair. So there's that pair of alternate interior, and then there's this pair. Oh, these are alternate interior angles. Cut. When we have coplanar lines cut by a transversal or intersected by a transversal. Now, if we know some things about these special pairs of angles, then we can know some things about L and M. And likewise, if we know some things about lines L and M, right? If we have some facts, if we got some truth about these coplanar lines, then we can also come to conclusions about these special pairs of angles. So that is where we're going with 17 and 18, or at least I think 17b. That's what we start with. Okay, let me get that ready. Okay, it says here, prove that the bisectors of adjacent angles are perpendicular. That's number 17. Okay, 17. Prove that the bisectors of adjacent angles are perpendicular. That's a symbol for perpendicular. Okay, the bisectors of adjacent angles. Well, there's something they're leaving out here. The only way this can possibly be proven is if these adjacent angles are a linear pair. They have to be. All right, that's the only way this can be proven. So adjacent angles that are a linear pair. So that means they're talking about a line like this. And then along that line, pick any point along that line and just put a ray from that line. There's your random linear pair. They're adjacent. This angle here is adjacent to this angle. These angles are adjacent to each other. They do not share any. These are interior points. Points on the interior. Remember we talked about primitive notions in relations like betweenness. It's like an undefined term, kind of, to say something is between. We could also say like same side. Same side. Like same side of a line. 2 points are on opposite sides of a line. That's also a primitive notion. That's what we mean by interior points. Define those by what side of these lines are these points to be found. So these are adjacent angles. Now, because this is a line, they're supplementary. They're called a linear pair. Okay, so you can have adjacent angles that are not a linear pair. And if that's the case, this is impossible. Can't be proven. Okay, so we're going to assume it's a linear pair. Let's see here. 17. Let's get to doing 17. Prove that the bisectors of adjacent angles. So we'll just randomly put this, randomly give us a line. So what are we proving here? So we have this line. Let's call it, maybe we should call it L. And I'm going to pick a point on it. Call it Q, maybe. Point Q. And then let's pick any point anywhere in the plane. Say like maybe call it R or something. And then make a ray. Okay. I could have rolled dice for that. Right? This is just this is any angle. I did not use a protractor. I just a straight edge, throwing a dart at the board, picking a point. Okay, so now the angle bisectors. So we'll bisect these angles. So that's what they're talking about doing. We'll bisect these angles here. And we'll just have a look at this random linear pair of angles. Totally random, right? Okay, let's connect these points here to Q. Now, what we're proving, what asked us to prove, is that any linear pair, just like this random linear pair, these adjacent angles that I just made, any linear pair, the bisectors of the adjacent angles in a linear pair will be perpendicular. That's what we're setting out to prove. Right there. All right, so we'll go about that. Say like this. Let's see, supplementary angles. Supplementary angles sum to 180. Complementary angles sum to 90. So if we can show, let's say, let's call this angle, if we can show that beta and alpha, if we can show that they're complementary, then let's call this point A. Let's call this point B. And, well, we could even say, call this L and call this M. If we can show that alpha and beta are complementary angles, then L and M are perpendicular. So we need to show that these are complementary. So, well, we can look at this and know that this angle is measurement alpha. By our construction, that angle is also alpha. And these are adjacent angles. We know that that's also beta because that's an angle bisector. And we know that this sums to 180. We know that beta plus alpha equal 180. This is 2 beta plus 2 alpha equal 180. Now, if this is true, and it is, this statement is true, then I can do anything I want to manipulate, like, say, this side of the equation, as long as I do the same over here, and the resulting statement will still be true, will also be true. Whatever I get, so I'm going to multiply both sides by 1/2. And because this is true, when I multiply each side by 1/2, the next statement will also be true. So I'll just put this 1/2 through here. 1/2 times 2 is 1, so we just have beta, plus 1/2 times 2 is 1 alpha, and 1/2 times 180 is 90. Beta plus alpha is 90 degrees. Therefore, beta and alpha are complementary, which implies M is perpendicular to L. That is 17. Okay, that was actually 17A. All right, so now I'm going to do 17B. And that's the puzzle book. 17B. So 17B, it says, prove that the bisectors of alternate angles are parallel. Prove that the bisectors of alternate angles are parallel. Okay, now, I don't know if maybe something is lost in translation. My Polish isn't very good. But there's an assumption here. We're talking about a special pair of angles, right? Alternate angles. So that means, so because they use the word alternate angles, we're talking about a transversal. We have two lines cut by a transversal. Okay, and what they're asking us to prove, I already know that it's impossible, and you may already know this as well, just intuitively, that it's impossible to prove this unless A and B, these lines here, are parallel. Meaning that these lines here, so they're talking about alternate interior angles. So here we have A and B, lines A and B, and we'll cut them with a transversal, right? Just let some random rotation, it doesn't matter. We'll just say like this. There we are, that's T, transversal T. So we're going to take the bisectors of these alternate interior angles. Let's assume interior angles. And we have to assume that A, that's a given. Okay, so this is given. A is parallel to B. Has to be the case if we're going to prove this. Because alternate angles, you get those, it's a special pair of angles you get with a transversal. But A and B, they only have to be coplanar. They could intersect. It's easy for lines in the same plane to intersect. So to have a transversal in the general definition, all you need is coplanar lines being intersected by that transversal line. And so we're going to assume that it was given to us. It's the only way that this is provable. It's the only way. Okay, so let's just to see what they're talking about here. Let's go ahead and bisect these angles. I'm going to also assume not alternate exterior, but alternate interior. Oops. Shoddy construction, maybe. Right here. And then one more mark. Bisecting these angles. Oops, got that side already. Okay, almost didn't get this intersection there, but so these bisectors. Raise through here. There we go. There's our angle bisectors. We're going to prove, let's call this ray, this ray is on a line we'll call L. This ray is on a line that we will call M. And we're going to prove, given this, prove M. Oh, that's wrong. What am I saying? M. I was thinking about the last problem. How'd that pop into my head? M is parallel to L. Oh, we're given more than this, right? We're given these angle bisectors. That's where M and L come from. Given this, make M and L, or maybe I should say L and M. L comes before M. Make L and M angle bisectors. Right, angle bisectors of the alternate interior angles. So this is the real setup, right? Given we have to start with parallel lines to make this possible at the end. So given these parallel lines, the transversal, you got these alternate interior angles, bisect them, and then those rays show that they're parallel. Prove that those are parallel. That is the task. Okay, you ready? We're going to prove that. So we're going to first do this. We're going to make L and M a different color. There's L and M. And these are angle bisectors, but these rays, they exist on a line. And I'm going to extend that line so that we can see something here. Oops, I bumped the camera. Okay, do you see it? Do you see it? Okay, so what we have here is, let's call this, well, we have T right here. This is, we'll make T orange now. T is a transversal of L and M. Now, we don't know L and M are parallel yet. We know that they're in the same plane, and we know that T is a transversal in the same plane. It's intersecting L and M, just as it intersects A and B, lines A and B. So there's L and M. We don't know if they're parallel yet, but we know T is a transversal. These are all coplanar. And because we have a transversal situation, Because there's a transversal, we have special pairs of angles. We have this angle here we'll call alpha, and this angle here we'll call beta. And these are alternate interior angles. We'll say alternate interior angles. Okay. Alternate interior angles. I want to make sure that here we can see everything. Okay. So here we have alpha and beta. They're a special pair of angles, alternate interior angles, because they are formed by this transversal across L and M, alpha and beta. Well, we know that this angle here is also alpha, and this is also beta, because we made them that way. I mean, this is why this is here. It's an angle bisector, right? So these angles are the same. Is right here because of their angle bisectors. And we also know that this angle here, that angle there, would be good. Would be good to give those names. But we can, well, just because we know where they came from, we can write this. All right, we can write alpha plus alpha equals beta plus beta. All right, because we were given that A is parallel to B. So A is parallel to B with this transversal. So we know that this pair of angles are equal. This special pair of alternate interior angles are equal because A and B are parallel. So this whole angle here is alpha plus alpha. This entire angle here is beta plus beta. So here we have 2 alpha equals 2 beta. And since this is true, anything I do algebraically, so if I multiply both sides by 1/2, don't divide, you multiply by the reciprocal. That gives me alpha equals beta. So alpha equals beta. Here's alpha. Here's beta. Alpha and beta are alternate interior angles. Let's say AIA. They're alternate interior angles. And alpha equals beta. Therefore, which implies L and M. Oh, let's say L and M are parallel. I could write that in English, but I'd rather just write L is parallel to M. Because remember we were talking about theorems? Where'd that paper go? Remember this theorem we had listed here? Alternate interior angles theorem. Right? That says that if you have a couple lines, Those don't look very parallel, but if you have parallel lines, if you have this, the theorem, this is a proven statement that these angles here are equal. That's the alternate interior angles theorem. So basically, if A is parallel to B, we'll say with T. All right, here's A, here's B, here's the transversal. If A is parallel to B with T, then A, IA are congruent. Oop, I ran out of space. Okay, now that's the alternate interior angles theorem. Now here's what you got to know. There's another theorem. And it's a theorem, so it's proven. And it has to be proven because what we're using the converse of this. So we're going backwards. We're going the other way. We're saying that we're saying the theorem we're using is if, right? At the end here, what this is if alternate interior angles are congruent, then are congruent with, we'll mention T in there somewhere. So if alternate interior angles are congruent with this transversal, with this particular transversal crossing AB, then A is parallel to B. So this theorem goes that way, and then the converse of that theorem is also true. Now, this is like an if-then, a conditional, right? Converse of a conditional is not always true. It's not. Like if it's raining, then the street is wet. The converse of that statement is not necessarily true. If the streets are wet, it could be a machine came by or somebody had a hose or there's some other reason that the street is wet. So the converse is not necessarily true. We don't know it for sure. It might be. It might be the case, but we don't know just from the logic, just from the direction. The converse might not be true. So in this case, though, the converse is true. And we know it's true because it was proven. It was proven true. It's a theorem. So think of the alternate interior angles theorem. You have to think of it as going both ways. It goes that way and it goes that way. Or maybe just write it. It's that situation. So that is how we got to this last statement here. Alpha and beta are alternate interior angles, and alpha is equal to beta. We should want to be really clean and nice. We should label this properly so we can talk about this angle, this whole angle. Like maybe we'd call this whole thing here, maybe we call that theta. This would also be theta. Or we could even give it another name since it is a different angle. Maybe call it omega would be the better way. So we'd say theta and omega are alternate interior angles from L or from A and B. Oops. I see an L that doesn't belong. This L is, I was writing here. Make M and L bisectors. Okay, so that's 17B. So When we got theorems, we build theorems from other theorems. And so if you got a theorem, you should wonder, is the converse of that theorem true? Has that been proven? Can I use that? Because to write theorems, you need to use other theorems. You need truth. You need things that are proven, or if not proven, they're just accepted as true. Right? Like, they're just accepted as true. Like you have two lines and they intersect. How many points do they have in common? One. Prove it. No, it's just too obvious. It's like too basic. Where do you even start to try to prove that? Everybody knows that. It's the most basic. It's an axiom. We'll just accept it as true. It's so basic and we can't prove it. It's just, we're just going to have to just move on from there. We got to get started somewhere. And so we use axioms to build theorems. And once you have theorems, you can create other theorems. And oftentimes, well, I don't know if it's often really, but the converse is true. It's actually not often. It's not guaranteed that the converse is true. That's why the converse itself is a theorem. It has to be proven. But that has been proven. We know that. So that's what was used for 17b. If the alternate interior angles are congruent, you know, the ones being made by this transversal T across A and B, if these alternate interior angles are congruent, then A and B are parallel. They have to be. They have to be. It's the only way we can get this. Now, why? Why? Euclid's fifth. That's ultimately the reason why. We can go this direction, and then we can come right back with the converse and go that direction. Okay. We'll have a look at 18. Okay, 18. We'll do 18 in here. We're on page 45. And spoiler alert. All right? A spoiler alert. I won't solve it really quickly. I'll talk about what we're doing in the proof. So you can pause it if you get a hint and see if you can finish it. Okay, let's see what 18 says. Doing 18, we're on page 45, says triangle ABC is isosceles. So from this one word, we know some things about the triangle. So let's do this. I'm going to say, here's a point A. Just call that point A, and we'll call this point, make a point over here. We call this C. And we'll just draw a line segment there. There we go. There's AC. Now, we're going to make this a random trigon, random isosceles trigon. So I won't do anything about the angle, but let's see. This measures, it's isosceles, so we'll get something that looks kind of accurate. Right? This is a random length. I didn't know, whatever number I could make a segment of that number, but we'll just go to what looks like 10 and a half. So we'll do 10 and a half over here. See, I rotate a random angle because it doesn't matter. Right? Isosceles just means two sides are the same. So these angles, the base angles will be congruent. This angle could be anything. So as long as these two sides, so this is very random. We'll just pick something over here like this, at 10.5, about that, just so it looks. And you can do this in your imagination. You don't need to, so we'll call this B. And there's B, and of course we're talking about a trigon, not just an angle. So there we have ABC, triangle ABC, and we have AC is congruent to BC. That's what we got. That's what we're working with here. Okay, and it says prove that the bisector of the angle adjacent to angle ACB, so bisector, prove bisector, I'm just going to write this, adjacent to angle ACB, prove that the bisector, the angle adjacent to angle ACB is parallel to AB. There we have AB. Okay, so the bisector of the angle adjacent to ACB. So what they're talking about is, okay, we have this angle. Let's look at ACB. Let's make it just so we're talking about this angle. Okay, the angle adjacent to this is going to be what's called in a trigon, it's called exterior, an exterior angle to the trigon. And the only exterior angle adjacent to ACB, well, there's actually, you could make two, but we're going to use this one. No, I think there's one. So you get it by extending this line segment. Extend that line segment. So this exterior angle, AC, I don't know, let's call this ACD. ACD is adjacent to ACB. ACD is adjacent to ACB. Okay, we're going to prove that the bisector of the angle adjacent to ACB, which is, we'll just say ACD, is parallel to AB. Well, all that writing, I ran out of some space. Well, let's construct the bisector. We'll just construct it and have a look. This is randomly made because of the way it was made. Now, the reason, what we'll do with the proof, the logic, is going to prove for every possible trigon, isosceles trigon, this is the case. Everyone in the universe. This diagram here is just helping us figure it out in our mind. And it gives us, because we sketched it out kind of randomly, it lets us kind of use our intuition to see that this is the truth. Right? Is this true? Is what we're going to prove? Do we believe it? It might help to prove it. We believe it. Okay, there we go. Right, this is the angle bisector right here. So this right here, there's the angle bisector. That's the ray. That's the angle bisector. And here's AB. We're talking about this. So let's call, no, we can call this okay, we can, let's see, we can, maybe we'll do this. Put a point out here, call it Q. And say, do we have enough labels? Okay, so we are to prove that this angle bisector here, QC, prove QC is parallel to AB. Okay. Well, we know, well, let's call this alpha and just give some names to things. Well, we call this alpha too, right? This is an angle bisector. An angle bisector. So here we have alpha and alpha. We know those are equal. What else do we know? Well, this is an isosceles triangle. With AC being equal to BC, right? We have this. That's the case. Right? AC and BC, those are the same. Those are congruent, same size. So we know that this angle and this angle are congruent, don't we? So let's call this beta, and we'll call this beta. Since they're the same measurement, they're congruent. We know this from the given. That's how you would justify that. Those are given. So this is the unknown. Let's call this, we don't know anything about this other than, some basic arithmetic. So let's call this X, right? And we know that 2 beta plus X, 2 beta plus X equals 180 degrees. We use this number 180 because of, why? Because of Babylonians. They like 60 for some reason. That was their favorite, that was their lucky number, was 60, Babylonians. That's why we're calling it 180. But the reason we can say that it's 180 adds to a straight line, basically, is because of Euclid's fifth. Euclid's fifth axiom is why we can write this. All right, so we have 2 beta plus X equals 80. All right, what else do we know? Well, we can see that this adjacent angle here that we bisected, right? It's an exterior angle to this trigon, to this isosceles trigon. It's an exterior angle to this trigon. And we know that it's adjacent to X, adjacent to ACB. And in fact, we know that ACB and ACD are a linear pair. They're a linear pair. Means they're supplementary. So, and we would measure ACB, let's say the measurement of angle ACD equals, well, alpha plus alpha. As we bisected it, and we called this alpha. So we had the same thing over there. So the measurement of angle ACD is 2 alpha. And so ACD, because it's a linear pair with ACB, these are linear pairs, we know they're supplementary. So that means 2 alpha. Supplementary means adds to 180. These are supplementary, so 2 alpha plus x equals 180. So we have 2 equations here. So with these 2 equations, we have 2 beta plus x equals 180. So that means that 2 beta plus x plus the opposite of x equals 180. 180 plus the opposite of x. So this gives me 2 beta plus, well, something in its opposite is just 0. So this leaves me with just 2 beta equals 180 plus a negative x. That means beta is equal to 1/2 180 minus, oops. I'm sure I'm in a hurry to write 180. Forget the 0. 180 minus x. Right? That is what beta is. Has to be. Okay, and we also said 2 alpha plus x equals 180. Isn't that right? 2 alpha plus x. We know this is a linear pair. So let's solve for alpha. What could alpha be? Well, let's skip a few lines. We'll say 2 alpha is 180 plus the opposite of x. 2 alpha equals 180 minus x. Multiply both sides by 1/2. Like that. And we have alpha. 1/2 times 2 is just 1. So we have alpha equals, I'm going to move this 1/2 over to this side just because I want it to be obvious that this is the same exact thing as this. And that means that alpha equals beta. Let's see how that helps us. So, therefore, alpha equals beta. So alpha and beta, we can see that we have line QC, and we have this line AB, and, well, wouldn't you know, they are cut by a transversal. Let's give it its own color here. Its own special color. Maybe we'll highlight it, huh? So there's our transversal. There's our transversal. And we have alpha and beta being equal. We could also see that alpha and beta are alternate interior angles. So therefore alpha equals beta, and since alpha and beta are alternate interior angles, AB, comma, AB is parallel to QC. And that's what we set out to prove, because QC is this angle bisector. That's how we constructed it. That's what they asked for. Trigon ABC is isosceles. AC equal to BC. And prove that the bisector of this exterior angle here, this exterior angle to the trigon here, prove that that bisector is parallel to AB. And that's just what we did. How did we do that? Well, we thank Euclid's fifth. For one, Euclid's fifth axiom, totally unproven. We just accept it as true. We're using that axiom, and we're using this like we did on 17b. So let me just show you a cleaner version of that. Okay. So given coplanar lines A and B intersected by a transversal T, and then because we have coplanar lines A and B intersected by a transversal T, we have special pairs of angles. We have corresponding angles. We have alternate exterior angles that we can identify. A couple pairs of those. And there's also a couple pairs of alternate interior angles. We'll label those, one pair of those, alpha and beta. Okay, so this is given. This is the let. This is the imaginary part. This is where a mathematician has all the power. This is just suppose. Just use your imagination. Fantasy. Set up this situation. Well, given this, if we're given this situation, we have some theorems from that. These are proven statements. So here's the proven, this is the situation. So here's the proven statements. We have this one. If A is parallel to B, alpha is congruent with beta. Oops. Let's say then. Red does if then. Do your math in pencil. That's what erasers are for. If A is parallel to B, then alpha is congruent to beta. So this was proven. Now watch this. We'll go the other way. If alpha is congruent to beta, then A is parallel to B. And this had to be proven. It's not enough just to prove this. You can't just automatically go the other direction. This way, the converse has to be proven. And they have both been proven. You can accept that. You can find the proofs. But in our book of puzzles, in this, it's already done, already proven. And that's how we got there. That was 18 that we just did. Okay, so this is the situation. Right? Given coplanar lines A and B, you have a transversal T, and then you have alternate interior angles, alpha and beta. That's the situation. Well, if A and B are parallel, then alpha is congruent to beta. And if alpha is congruent to beta, then A and B are parallel. Both those are theorems. So you need to know that you have those. Those are tools in your toolbox to win these games, to write theorems, to prove things. Okay, that is 18, or that was 18. Okay, here we go with 19. Okay, number 19. Let's see. It's talking about an isosceles trigon. Isosceles trigon. An isosceles trigon with a vertex, they call the vertex angle. Call that alpha. That's a squiggly alpha. That's a better shape than alpha. I really should erase, but I'm not going to erase because it shakes this whole table, messes with the camera. Is it even still focused? I'm going to check here to see. Yeah, okay. Gosh, it'd be horrible if I was filming all this. I was out of focus the whole time. Okay, so isosceles triangle, the vertex angle is alpha. And they say, what are the other angles? Isosceles triangle given vertex angle alpha, what are the base angles? So the two angles, what are the base angles? So the two angles that are congruent at the base of the isosceles triangle. So let's just do it like, I don't really have space going this way, so we'll make it the length of this straight edge. It's a random angle there. So these two sides are congruent. So these angles, no, it would look more like a base if it was like this. Oops. And then it'll be our base, isosceles triangle. So base angles, this would be the vertex angle. So they give us the vertex angle alpha. What's the measurement of a base angle? And 19, it says when if alpha is 15 degrees, then a base angle, or it says calculate the measures of the remaining angles. So it's plural. So that means you should list your answer. It's 180 minus 15, right? So that's 165 is what's left from 180. These are equal. So take 165 in half. That would be what? 80 would get us 160. 82.5. Right? 82.5. Check my arithmetic. Then a base angle is 82.5. And when the vertex angle alpha, that's like, whoa, that's really, it's obtuse. It's an obtuse angle. If it is an obtuse trigon can also be isosceles. Remember, isosceles talks about the number of congruent sides, two congruent sides. Then we have ways to talk about the angles. And if you say obtuse, it means there's one angle greater than 90. That would be, so if alpha is 115, alpha 115 implies remaining angles. We'll do it just like the English translation of the Polish. Remaining angles measure well, 115 minus 180. How many degrees are left? 65? So if this was 115, so if this is way up here, if it was 115, that'd take up 115 out of the 180. That leaves us with 65 degrees left for these two base angles. So 65 divided by 2, 32 would give us 64, so we got to go 32.5. Measure 32.5 degrees and list it twice because they ask for each angle. If you were just writing it on my exam, you could say then a base angle is 82 because the base angles are congruent. But I suppose they're asking you to show that you know that isosceles means these two sides, but because you have two congruent sides, you do have two congruent angles. So that's why they want you to list all three of them, to show that you know that. Yeah, that is number 19. 20. Are you ready? Here we go. Make sure the camera is in focus. Okay. So 20 we're given an isosceles trigon. This is 20. And then they give us two situations, A and B. And it's a relationship between the vertex angle and the base angles. So for A, they say the angle at the base is 4 times smaller than the angle between the arms. So that means, so let's call, start here. Let, the most powerful word in mathematics. And remember, it starts with the letter L. So does label. So let's let, we're talking about an isosceles trigon here, so let alpha be the vertex and beta be a base angle in this isosceles trigon. So situation A, they say beta is 4 times smaller than alpha. That means it takes 4 of them to get an alpha. And in situation B, for an isosceles trigon, they say the opposite. They say the angle at the base is 4 times greater than the angle between the arms. So one of a base angle, beta, is 4 times greater than the vertex angle. So it would take 4 alphas to get 1 beta. All right, that's what we got going on. So, thanks to Euclid's 5th axiom, because of Euclid's 5th axiom, the 5th, because of Euclid's 5th axiom, we have a theorem that says all of these angles in any trigon add up to 180 degrees. 180, this particular number, because of Babylonians, adds up to a straight angle. Adds up to a full line. 180. Babylonians, their favorite number was 60. So that's why we have that. But Euclid's 5th axiom is what gets us this theorem. And this number just This number is just for tradition only. It's only there because of tradition. Okay, so we know that. So that we know that if we take a base angle of a isosceles trigon and we add it twice, because two angles are the same, and then we add the vertex angle, we'll get 180. We will get 180. And we know that alpha is equal to 4 beta. So we have 2 beta here, beta plus beta, and we'll substitute this alpha for this 4 beta. So 6 beta equals 180. A measurement of one of the, we'll multiply both sides by 1/6. Multiply both sides by 1/6. Do not divide. Multiply by a reciprocal. This reciprocal. Because we want to turn this into a 1. So we can say 1 times beta, which is just beta. We multiply by reciprocals. So beta is equal to 30. So our angles in situation A for this isosceles trigon would be 30, 30, and 120. Oops. Got a G or a 6 there. I'm not sure what I was right. 120. It's like that. So here we go with B, situation B. Spoiler. I'm going to do this. Pause the video. Do not watch. Figure it out for yourself if you can. Because the solution will only help you if you've already tried the puzzle with your own brain. You got to frustrate your brain. So here, the same situation. We take a base angle, take the other base angle, and then we take that vertex angle and we get 180. Right? But here we know that beta is equal to 4 alpha. So we have this beta plus this beta angle plus alpha equals 180. So we're going to substitute in here. So each beta angle is actually 4 alphas. So here we have 4 plus 4 is 8, plus another 9 alpha equals 180. Here, alpha is equal to 20. So the vertex angle would be 20 degrees. And that leaves us with 160 left over for the base angles. And those base angles are the same. So we have 160 left over. Our base angles are 80 and 80. That is number 20. Okay, 21. 21, this will be 21A on this side. And we will use the colors in the book. This is the puzzle book. We're still on page 45. Where is it? Right there. And let's see, they give us 21A, they give us this. We'll use textbook colors or workbook colors. They give us this figure. So here, this theorem is pretty straightforward. We just need to find these angles. So the given, they don't use words. They just use the figure. They use symbols. So I say this and this and this. So all these sides are congruent. And they say this is 40 degrees. They want us to find alpha here. Now, there's lots of ways you can reason to go about it. But basically, this figure is the given. So given this situation, if this thing, then alpha is some measurement, what we're going to find out. And so this will be a proven statement, or a statement proven true. We might not justify it in detail. But we know that, let's see, so this is an isosceles triangle. Here are the arms, so this is the vertex angle. Here's a base angle with the other base angle. We know the base angles are equal, so this is also 40. So, most powerful word in math, let. Let me make sure the camera is working. Camera, yeah, okay. I want to make sure I got the whole page in view. So here's 40. So that's got to be 40. So that's 80. So all that's left, thanks to Euclid's fifth axiom, gives us the theorem that trigons add up to 180 degrees. So this is 100 degrees. That's all we got left. And we can see that, well, this is a linear pair. That's one thing, we have to assume, right? Because this could be, slightly off? I mean, maybe this wasn't a line. Maybe this was a vertex. We're going to assume this is a linear pair. So that means alpha here is 80 degrees. 80 degrees. Alpha. Now we could have reasoned that another way, I suppose. But that's the fastest, most obvious one to me. Because you can see that you could look at it this way, I suppose. Let's see. Oops, I should write a sketch it like this. Okay, that and this. Oh, no, that's not true. I was marking these arms because these aren't equal. This has this extra. This ends. You see. Yeah, this ends right here. Only that pertains to that part of it. So alpha is 80. That's 21A. Let's do 21B. This page 45 in the workbook. Book of Puzzles in Plane Geometry. Games in Euclidean Space. Here we go. So I started with this. We'll use the same colors as the workbook. Give us a figure like so. Like that, and like that. All right, and then they tell us this is what we got, 21B, and they say this is a situation here. So those sides are congruent. So we got an isosceles trigon here. And then they say this is also congruent with that side. And they ask us to find alpha after giving us this angle here, 70 degrees. Okay, so let's see. So if this is 70 degrees and we have an isosceles trigon here, then here's the arms. This is the vertex angle. That's the vertex angle. So these are, we'll call them the base angles. We'll use beta for base angles. Beta, beta, base angles. So they're equal. So we have this is 70, right? And, well, we can see that this right here, this is a linear pair. A linear pair. These are supplementary. These adjacent angles, because these adjacent angles, this angle here and this angle here, because they're adjacent angles and supplementary, they share this line here. They're a linear pair. We know they're supplementary as a linear pair, so that means we get what's left out of 180 when you take 70 away from it. All that would be 180, so this is 110. So we can see that this here, this is also an isosceles trigon, because this trigon here has got those arms, and we have 110 here. 110. That means we have how many degrees left over for this trigon? 70. And we have to split them equally between the base angles, which over here we'll call alpha. And we're supposed to find alpha. So we have 70 degrees left over between these two, which are congruent. 70 divided by 2, alpha is 35 degrees. That was 21B. And 21C. Again, we'll use the workbook colors. Make a figure just like in the workbook. They do that. Something like this. Something like it. Then make a figure like that. 21C on page 45. Of the workbook. Puzzle book. Technically, workbook. I like to think of it as a puzzle book. Puzzles and plane geometry. Okay, here we go. What do they tell us here? Oh, again, isosceles trigon. Like that. We have a couple isosceles trigons. They tell us this angle is 20 degrees here, and they want us to find alpha. Sitting right there. So let's go about that. Let's see. So here's a vertex angle. These are base angles of this isosceles trigon. So they're congruent. So that's 20. So that what's left over, 20 and 20 is 40. Take that away from 180. And you have 140 left. So this angle here, this vertex angle of this isosceles trigon is 140. And we can see that this, again, right here, we have a linear pair. So these are supplementary angles. They're adjacent and they're supplementary. They're supplementary because it's a linear pair of adjacent angles. So that makes this angle 180 minus 140, 40. And this 40-degree angle is the vertex angle for an isosceles trigon. So the vertex angle is 40. That leaves 140 left over because thanks to Euclid's fifth axiom, the physith, thanks to Euclid's fifth axiom, this adds up to 180. So 140 left over between two congruent angles. They have to be 70 each. That's 70. And so our alpha angle is 70 degrees. And that was 21C. Okay, here we go with 22. 22. All right, let's see here. They give us a figure like this. We'll do the orange just like they do. Lots of orange lines all over the place. Just draw the figure, then we'll write what we know. Here they give us a figure, and they give us some spoken language, or some words, sentences, statements. So we have some statements in our given, more than just a figure. And they give us a figure like that. And see how they say this is A. Here we have B. This is C. This is D. This is E. And they tell us, let's say AB is equal to BC, and the measurement of CD is equal to the measurement of DE. Prove that the lines, let's say given, we're given this. Prove that the lines AB and DE are parallel. So given this, prove, I'll write this here, prove AB is parallel to DE. Okay, here we go. Oh, they give us, let's use this information to mark our figure. AB and BC, same measurement, and CD and DE are the same measurement. That means we can say this is alpha as an isosceles trigon. Make sure I'm have this in view as an isosceles trigon here. These base angles are the same, alpha and alpha. Oh, and look, this is a vertical angle, right? These lines, so vertical angles are congruent. So this is alpha and alpha. This has to be alpha. And we're looking at this isosceles trigon here. That's got to be alpha. This angle too. So we know that much. So we were given just these, and from that we could determine these angles, right? And we started with just a label, right? It's the same thing as let this angle be alpha. A lot of times that's all let is. Suppose or if. Sometimes these English words fit better than let. But let is the most general, the most universal. The label things. Let this angle be a symbol of my choice. So I called it alpha, and because I saw the isosceles trigon here, I know that this is a base angle of this isosceles trigon. So that's also alpha. But I see that this is a vertical angle to this, so that's also alpha. This is an isosceles trigon. So that means the base angles are alpha. One of the base angles is alpha, so this other angle here is also alpha. Okay, now here's the thing. Okay, we want to show that A and AB, let's give these, we want to prove that the blues are parallel. Oops. It's kind of off, but let's pretend that's right on. Let's pretend I changed that orange to blue. Prove that those are parallel. Well, let's see. To do this, we simply have to refer in a different way. Because these are the same measurement, but they aren't the same angles. So we need to talk about these angles differently, in a different way. So we just mark them down as measurements. We need to refer to names here to prove. Okay, so we'll say that angle, so for the proof, we'll say that angle BAC, angle BAC and so there's BAC, this angle here, we're talking about this alpha. This angle here, BAC, and this angle here, CED. Put the vertex. It's the middle. You could call it DEC or CED, as long as E is in the middle. So CED, angle BAC and angle CED are alternate interior angles. I'm just trying to save a lot of writing, right? So this is a whole nother, that's a whole nother let. That's like let AIE be the same thing as alternate interior angles. And even this, right, is so BAC and CED, we can see that because AE, we'll say AE is a, show you, AE, that line there, that's a transversal. So we have, here we have AB and we have DE, two coplanar lines. Coplanar lines are in the same plane. Two coplanar lines, and they're cut by, oh, that was the wrong transversal. Two transversals here. We're going to use this transversal, AE. Two lines cut by a transversal. Now, because we have that situation, we have alternate interior angles. Now, these alternate interior angles, this special pair of angles we're going to talk about, are BAC and CED. Right there. AE is a transversal. To AB and DE. Yeah, this is messy. AE is a transversal to AB and DE. Right, that's why I'm calling BAC and CED alternate interior angles. They're a special pair of angles. Now, we know the measurements, so we'll say the measurement of angle BAC. Oops, I should write it like that. The measurement of angle BAC equals alpha, and the measurement of angle CED, we can see is also equal to alpha. by the converse of the alternate interior angles theorem, which is its own theorem. Theorem. Because these are equal by since the converse is true, we'll just refer to this alternate interior angles theorem. By that theorem, AB must be parallel to DE. Okay, so this is another time. Oh, I stacked all those papers away. Well, this is another time we went the other direction. Okay, here we go. 23. 23, is that right? 23. This is the puzzle book. Dropping rulers. Let's see, we're on page 45. 45, yep. We're doing 23. That one right there. 23. Okay, ruler picked up. Okay, prove that alpha is equal to beta. So let's see here. I'm going to use like the American convention and do that for right angle instead of the arc dot. If this is right angle, right, then these are vertical angles, so they're congruent. So the other way to write right angle is like this. But I write that for like any angle. It's like for an angle you can write that dot inside. You write two marks. You can do two things like this to differentiate between angles. And so I'm going to use the square thing and or the corner thing. So we got that, and we got that. That's a given there. That's given. Square there, and we're told that this is alpha. Oh, this is 23A. Well, I don't think they have A, B, and C. I think they have three figures for 23. So here's alpha, and they say this is beta right here, and prove that alpha equals beta. Okay, well, we know that, look at this, a tetragon has four sides. 1, 2, 3, 4. 4 sides is a tetragon. We know that a tetragon can easily be made into two trigons. And trigons add up to 180, so you have 180 here and 180 here. So thanks to Euclid's fifth and some theorems that come from it. So Euclid's fifth, so we get triangles add up, the angles on a trigon add up to 180. So tetragon, they add up to 360, because we got every tetragon is made from two trigons. So this is 360. 90 and 90 is 180. So we have 360 total in here. This angle here, that angle is going to be 360 minus 290s, which is 180. So there's 180 left. Right? So this angle is 180 minus alpha. 180 minus alpha. And what else do we know? Oh, well, this right here. Here we have a linear pair. This is 180 minus alpha. Oop, I got straight edges dropping all over the place, okay? So we got that. 180 minus alpha. Let's see. What else can we infer? Or what can we deduce? So actually, we have everything we need right here. Just need to call this something else. So let's call this omega. And this angle is omega. So omega equals 180 minus alpha. We know that, right? Omega is also a linear pair with beta. So omega is equal to, it's also equal to 180 minus beta. So we have two equations here. We have omega is equal to 180 minus alpha, and omega is equal to 180 minus beta. So we would just set those equal to each other. 180 minus alpha equals 180 minus beta. Add the opposite of 180 to each side. Opposite of 180 to each side. And then we have negative alpha equals negative beta. Multiply each side by negative 1. Then we have alpha equals beta. So here we would say omega. So it starts by saying, let. Well, geez. To be specific, we'd want to give these names points like this. Call this A here. This call this point. Call this point B. You would say angle ABC. Make that C. Angle ABC is supplementary. It's a linear pair with beta. And that measure is omega. As a linear pair, omega is 180 minus beta. And then we would refer to A, B, C in this tetragon by the theorem. I have to cite that. Let's see, here we go. Right, they got quadrilaterals, tetragons, somewhere in here. We got that. That's ours to use. We don't have to prove that. It's already been proven. Okay, it's not in this book. It is in the course book. So already proven. You don't have to prove that. So we have 360. So anyway, that's where we get that. All right, let me set those equal together. That is the first one on 23. Here's the second one. Wait, is this right? Yeah, okay. Here's the second one. This is also 20, 23. Gosh, is my camera in focus? It's not so bad. 23. So on 23, we want to find, they say this is alpha, that angle right here. That's alpha. They say this is a right angle, and this is a right angle. Right angle, and this is beta. Okay, so let's show that beta is equal to alpha. How do we do that? Okay, well, here we have a tetragon. We know that this is 90, so this has to be 90. And once again, look, we have this tetragon here. So all these angles add up to 360, but two of them are 90. So that means we have 180 to go. And we have beta here, so this is 180 minus beta is right there. 180 minus beta. And we can see that this angle here has a vertical angle. There it is, right there. There's alpha. And like before, let's call this angle, let's give it a name. Let's call it omega. This is the angle omega, and we'll say its measurement is 180 minus beta is omega. So omega is 180 minus beta. Alpha, and then we have omega is also, because this angle is omega, and I'm talking about, no, I use blue. So this is, we just call this omega. This angle. Okay, that's omega. So see, we're doing this with lead. Label. So we call that omega, and we note that it must measure 180 minus alpha, or I'm sorry, 180 minus beta, because it's part of this tetragon. And two of the angles in the tetragon are 90. 90 times 2, that's 180 from 360. So we have 180 left with this angle beta. So omega is 180 minus beta. Now, we also know that omega is a linear pair with this angle here. Now, let's see, let's call this, oh, well, we know the measurement's alpha. We could call it something else. We could call this data, but that would just, all that would do is add a couple extra lines of algebra. We'll just leave it at alpha. So because omega and theta here, omega and theta are linear pair, form a linear pair. We know that they're supplementary. That omega is 180 minus theta. But theta, we know, is a vertical angle to alpha, so it's 180 minus alpha. Therefore, I'll skip the algebra. Therefore, beta equals alpha. That's 23. That's the second one on 23. There's one more. How does it go? I think like this. Okay, let me say we got a right angle here and a right angle here and right angle here. And they're telling us this is alpha and this is beta. Show that these angles are equal. Okay, let's see here. What do we know? So again, right, we can see a tetragon. A tetragon is just, it's two trigons. You can always draw a diagonal because a tetragon has 4 vertices. You can always draw a diagonal, and that's going to give you 2 trigons, and they both add up to 180. So 2 times 180, you have 360. So we have that theorem from the triangle theorem of 180, thanks to Euclid's 5th axiom. So beta. Do we need this angle? Well, look, this is a linear pair. So we know they're supplementary. This has to be 90. Same here. And same here. This is a vertical angle. I really don't think I'm going to use this angle, but just label, 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 label. Oh, look at this. You got a vertical angle here. Here's beta. There's beta as well. And we have 90 alpha. This angle here. Do we know what that angle is? Let's give it a name. Well, let's call it theta. So that's theta. So we have here, we can write this equation like this. We can say theta plus beta plus 90 equal 180. So theta plus beta equals 90. Right? So all I did was let in the form of a label. I just gave something a label, just like these. Well, these I'm just kind of declaring measurements, right? These are just indicating a measurement, not quite as powerful in your diagram. I mean, it's a label. You're marking this as like 90 degrees. These are right angles. These are right angles, but it's not as powerful as a label. When you give something a name, that's powerful. Let's look what it lets us do here. All right, we saw theta plus beta plus 90 is 180. So we know theta plus beta is 90. Now here we have a trigon. And we see it's a right trigon. A right trigon. It's got a 90-degree angle. That means these two angles have to add up to 90. That means theta plus alpha equals 90. Therefore, alpha equals beta. Okay, this result, this happened, just giving this a name. Okay, this was 23. Okay, 24. Here we go with 24. Let's see, is the camera focused? Is the camera still focused? Seems to be. Okay. It's 24. We got this situation. Now, I think we have to assume something. We have to assume some physics. So what we're supposed to, they give us, so this is billiards. And they say this point here is M. And this point here is N. That's where it collides with the sides of the pool table, M and N. And we're supposed to show that, let's say this is A, and let's say this rebound, that's B. Let's call this C. Show A, prove A is parallel to C. Prove A is parallel to C. So we're given this situation, but we're also given something else by physics. And we know that the reflection, the ricochet, these angles are always congruent. Now, we have to assume some other things. We have to do this, we have to assume that we can use some physics, and we have to assume that this ball is hit straight. It's not spinning in any way that would change these angles. So once we have that, though, we know this angle, those angles are congruent. Okay, so let's get to it. I think first thing we should do is maybe extend some lines so we can see we need to find angles. We want to prove A is parallel to C. So if you remember, it goes both ways. So if we have coplanar lines, A and B, here we're going to say A and C. Now, let's call this B. We'll call this B because we can do what we want. I can change my mind. So can you. Let's call this X. I don't think we're going to use that. Oh, here, let's call this TX. What am I saying? Let's call this T. Why T? Because we see A and B. We see A and B as coplanar lines, and T intersects them both. So T is a transversal. It's transversal. Line T. Okay? And if we have coplanar lines, A and B, intersected by a transversal T, then we have alternate interior angles, alpha and beta, right? Those are, that's a special pair of angles. So let's, alternate interior angle. So let's say this then would be, let's extend this line this way. So this would be an alternate interior angle to this. We could also use corresponding angles, but let's start with alternate interior. We'll call that alpha. We'll call this beta. It's just not as clear. Well, it's not as clear because this thing right here, all of this is alpha. And here we have this beta. So we'll have to figure out what that is. Okay, so either way, so we have alternate interior angles, alpha and beta. If A and B are parallel, then this special pair of angles, this special pair is congruent. If also, this is something that was also proven, if this special pair of angles is congruent, then A and B must be parallel. They have to be. Okay, so this is a, so I would say this is the alternate interior angle theorem. This one right here starts with parallel lines, and then this is the converse of that theorem, which is itself a theorem that was proven. So this converse had to be proven. And it was, so we can use it. Okay, so let's see. One thing we know in physics is that these angles are equal. So this is alpha as well. So here we have this angle here. This is, since we have these angles here, supplementary. All right, this is a line. So we have 180. This angle here is 180 minus 2 alpha. That's 180 minus 2 alpha. This is beta. Here we have alpha in here. Oh, we know this. We got a pool table. We know we got a right angle here. We have a right angle here. Wait, we can't call this alpha. This is wrong. Okay, so here we go with 24. 24? Yeah. So 24, we have to assume something. We're going to use something in physics. And we're going to assume that this ball is not spinning. It's just hit straight on. Need to sharpen this pencil. Okay. So here we go. We're going to prove we should label some things. We want let's call this line A. This is B. We want to prove given this pool table situation, we need to prove A given that, prove A is parallel to B. Okay, here we go. We're going to use some physics here. We know from physics that angles, say that this reflection angle, the angle of reflection is equal to the angle of incidence. So the angle at which it hits this side wall of the billiards table. So it hits this wall, and this is going to be, we'll just call that alpha. Okay, this angle here, which is the angle of incidence, the angle at which this thing collides with the wall. This ball, or it could be a hockey puck, something simple in physics. It's this wall, it's going to ricochet, it's going to reflect, bounce off this wall at the same angle that it collided with. So that's alpha. So that's alpha and that's alpha. Oh, well, we can see here that we have vertical angles here, so this is also alpha. All right, and this is a pool table. So this is 90 degrees. We can mark that. I don't think we need to label it anything more. What else could use a name? We have alpha here, And let's see, we can call this angle beta. And we'll extend this. And this, we called this A and this B. Let's call this line right here, let's call this T. Why T? We can call it anything we want. But why not call it T? Because it's a transversal. Here we have A, line A. If that were to continue off the table, off the pool table, and go like that. And so this line T is a transversal. So what do we have? We have alpha, alpha, and this angle here. This angle here is 180 minus 2 alpha. That's 180 degrees. That's 180 right there. Two angles are measurement alpha, so we have 180 minus 2 alpha. That's the measurement of this angle here. So we need only okay, so here we have a 90-degree trigon, a right trigon, this 90-degree angle. So this angle here must be 90 minus alpha. Because thanks to Euclid's fifth, gotta keep checking the camera. So thanks to Euclid's fifth, this trigon, angles add up to 180. So 90 is being used by this angle right here. So that leaves us 90 left. 90 degrees left in this trigon. One angle is alpha, so this must be 90 minus alpha. 90 minus alpha. We're calling that beta. This is a vertical angle, so we could call this 90 minus alpha. That's 90 minus alpha. Okay, we're using physics here. So this angle here is equal to this angle here. That's 90 minus alpha. So this is 90 minus alpha. It bounces off this wall or this edge of the table at the same angle, 90 minus alpha. 90 minus alpha. This is a vertical angle here, so this is 90 minus alpha. Okay, this angle here is 180 minus 2 alpha. So let's say what we're going to do here is we're going to call this theta, this angle theta, and we're going to call this big angle, we're going to call that omega. Theta and omega. Okay, to label this properly, I should say, we have, call that point A, B, oh, they give us points. They call this M. Forgot to label that, M, and this is N. So to do this properly, call this point A, this point, a point here, call it A. This is line A. Capital B is point B. Little b is line B. Okay, so now we're going to say angle A M N, and so A M N, this angle, and angle BN say BN, I don't know, put a point down here, call it, I don't know, O. No, let's call it P. Make sure my camera is getting this. So an angle BNP so this angle and this angle are corresponding. Oops, I'm running out of room here. Corresponding angles. Okay, they're not alternate interior angles, but they are a special pair of angles. So we know that AMN is 180 minus 2 alpha. So, okay, maybe we didn't need those extra points. They gave us M and N. But theta is equal to 180 minus 2 alpha. All right, we know that. In this situation right here, angles of incidence is equal to the angle of reflection. Same here. We have a 90-degree trigon here, so we know that this is 90 minus alpha. These two are alpha. So we know this angle is the same as this angle here because the angle of incidence, as it bumps into this wall, it reflects at the same angle. That's the physics that's assumed here that we know. And we know that this is 90 minus alpha. Here we have a vertical angle, 90 minus alpha. So we look at omega, which we're calling, just to properly label it, we have to say omega, omega is equal to BN, angle BNP, just to be clear, because we got lines all over the place here. All right, so just to be clear, you want to do this. So angle BNP is equal to omega, or that measurement. And we'll say the measurement of angle AMN is equal to theta, which is 180 minus 2 alpha. And the measure of this corresponding angle, B and P, corresponds to AMN. This measurement is the sum of these two angles, 90 minus alpha, and this 90 minus alpha. So omega is equal to 90 minus alpha plus another 90 minus alpha degree measurement. So omega is equal to, well, we take the parentheses off here. We have two 90s, that's 180, two positive 90s, and two negative alphas, so that's 2 alpha. So here we have it. Omega is equal to 180 minus 2 alpha. Theta is equal to 180 minus 2 alpha. So by the same reasoning here, although we could say corresponding instead of alternate interior angles, say corresponding angles. With corresponding angles, In this particular case, we say with corresponding angles, theta and omega. That's what we're talking about. So it goes both ways. So because, I'll color in these angles, okay? So because this angle and this angle, those are corresponding angles because we have A and B. Gosh. Got pencils all over the place. We got A and B. Those are two lines cut by a transversal. Yeah, that is the situation. Two lines cut by a transversal. We know that these corresponding angles, those corresponding angles are congruent. Therefore, these lines must be parallel because they're coplanar, intersected by a transversal, which means they have special pairs of angles. The special pair of angles turned out to be the same measurement, the corresponding angles. So that means by the theorem, the converse of the corresponding angles theorem, these lines are parallel. So right, QED. That's what was to be demonstrated. Oh, it shouldn't be written here. It's prove. That's our instruction. QED needs to be written down here. Oh, this is a mess. I will do this in class, or we'll write this formally. All right. Okay, I think that's it for page 45. If you have questions, ask me in class.